All right. So we're going to kind of switch gears a little bit here today. And I'll try to relate it to stuff that we've already talked about, but it's be quite a bit different of a concept. So we'll be in here in Module 12, primarily focusing on game theory. Just some things before we get going. Those participation quizzes for this week, so the previous four and then today's as well, will all be due by the end of the day, Sunday. You also have that module, oh, there it is, Module 11 quiz, Module 10 quiz due by the end of the day, Sunday as well. I also put up the final module reading, so I'll make sure everyone can see it now. It should be set to release when class started on Top Hat. So that'll be due before we meet in class on Tuesday, so we won't start covering Module 13 until Tuesday. We'll start Module 12 today, finish it on Monday. We may start Module 13 on Monday if we have some additional time in class, just to give us more time. It's probably the densest, that's not the most dense of the modules that we'll go through. So I want to make sure we have ample time to go through it. I think we'll get through a lot of Module 12 today, so we probably won't need all of Monday's class to finish it. So we might start that, but the module reading won't be due until we start class Tuesday. Okay. I think that should kind of cover it in terms of housekeeping, unless there's any other questions for me before we just kind of dive right into it here. Okay. So Module 12 is primarily about game theory. So we're going to have some definitions that we'll talk about, and we'll kind of set up the structure of the games that we're going to look at. So game theory is ultimately trying to understand how individuals best respond to other individuals' decisions. So a Nash equilibrium is going to exist when we are both, if there's two individuals, there can be more, but for our examples, we'll keep it at two people, when we're both best responding to the other person's best strategy. Okay. So we're both choosing the strategy that's going to maximize, in the case of a firm, their economic profits, given what the other firm is doing. So we'll have a lot of examples that are market-based today. We'll also look at examples that games that aren't necessarily like firms making decisions, and we'll kind of see how these strategies can be applied to both scenarios. So, if you haven't seen or heard of the movie Beautiful Mind, this is about John Nash. He's the guy that really kind of revolutionized game theory in the context of how we apply it to markets. Interesting guy, had some mental issues, but it's a really good movie. And that's kind of the basis for, the guy that kind of put it, game theory on the map, so to speak. So our basics is we're going to have players, and then we're going to have rules of the game. So for us, it's going to be two-player games. We're not going to look at anything more than two individuals making decisions. When decisions are made, so are they made simultaneously or sequentially? So today we're just going to be talking about games and scenarios where people make decisions at the same time, right? Or we're making decisions without knowing what the other person is doing. Sequential is when I make a decision, you get to see my decision and then respond to it. So we'll talk more about sequential games on Monday. The strategies are just going to be the possible options that you have, right? The actions you can make. So in some of our examples, this will be like, can the firm set a high or a low price? Do I produce 100 units or 101, et cetera? Okay. And then our payoffs are going to be whatever the two strategy choices that the players chose, what are the resulting payoffs for that combination of strategies? So if we both set a high price, what are our profits? Or I always use like an example of the game of like chicken. Like if you're running at, if you play on the playground, we're both running at each other. We have to make a decision at the last second to either go left or right, right? We both go left, the payoff is bad. If one of us goes left, one goes right, the payoffs are good, right? Neither we won't run into each other, okay? So it could be as simple as that. So we're going to represent these payoffs in a normal form game matrix, so a 2x2 matrix. So let's say we start out with this market example where I have two firms. Those are my players. They're going to set either a high or a low price, okay? Each firm is going to enjoy the payoff of those different combinations. So we both set a high price, we both set a low price. One sets a high price, the other sets a low price, etc. Okay. So the way that we're going to write this out is we're going to put each player, right? Firm one or player one down here, firm two, player two up here. They have their two possible strategy choices. So either setting a high price or low price, high price, low price. We're then going to write their payoffs, kind of using this like little matrix here, where the lower left corner represents firm one's payoff and the upper right corners represent firm two's payoffs. So if we both set a high price, here would be like firm one's profits, and here is firm two's profits. If we both set a low price, here's the resulting firm one's profits, here's the resulting firm two's profits. Those will be different, right? If we're setting low versus high prices, that's going to change our profit amounts. Okay. So this is our payoff matrix, and this is how we'll kind of write all of these, even when it's not in the context of firms. Okay. So typically, we think of these simple game theory models we're going to look at applying to markets where we have a small number of firms, or we'll call it an oligopoly. So oligopoly just means few. So a few number of firms. More specifically, we'll think about duopolies, where we have just two firms. Okay. So some other terminology we're going to have is that if the firm's optimal strategy choice is independent or doesn't matter, doesn't depend on what the other person is doing, we're going to call that a dominant strategy. So if firm one, it's always better for them to set a high price, then that would be a dominant strategy. Even if the other firm sets a low price, it's still better for me to set a high. That's a dominant strategy. And we'll kind of identify these along the way. Okay. If both people have a dominant strategy, well, if I'm going to do the same thing regardless of what you do, we know what that equilibrium is going to be, or we end up with this Nash equilibrium, okay, or a dominant strategy equilibrium. And I'll kind of define this as we go through examples, that pointing out the examples we have where we do have dominant strategy equilibriums. Now, a prisoner's dilemma is going to be kind of this counterintuitive result, which is that if there's individuals can sometimes have a dominant strategy that results in lower payoffs for both individuals. Okay, so the idea that we'll kind of set with this, where this comes from, is the idea of two criminals being kind of put in separate rooms and asked about a crime. So that example will kind of set up thinking about we have two individuals, go away from this market kind of based example, thinking about an example of the prisoner's dilemma that exists outside of firms and quantity price decisions. So if I have Dan and Joe, two suspected bank robbers, if I don't have enough evidence to put either of them away for the bank robbery, but I've got some evidence I can put them away on lesser charges, maybe give them each 5 years if neither of them confess to this crime. And I put them in separate rooms and offer them the following deal, that if they confess and their partner doesn't, they get to go free. Right? So if you don't confess, but your partner kind of rats you out, right, you're going to get 25 years. And then if you both confess, well, we can't let you both go free. We won't, be able to kind of pin it on one person, but we now have enough evidence, right? We've got information coming from both people. We can put you away now for 10 years. Okay. So this is our setup. We could write this out as a normal form game. So we've got our two players, Dan and Joe, right? We've got their two strategy choices, which is that they either confess to this crime when put in this separate room, or they kind of don't confess. Okay. So those are our two different possible strategy choices that each individuals have. We're then going to write what the resulting payoffs are. Okay. So I'll build this out, kind of, you'll have it all here, but given the information that we had, we've got this kind of normal form game matrix. So if we both confess, we both got 10 years in prison. If we both didn't confess, that's where we both got 5. If Dan confesses, but Joe doesn't, well, that was the situation where the individual who confessed gets to go free. They pin it all on the other person, they get 25 years. If Joe, I forgot my S. If Joe confesses, but Dan doesn't, Dan gets the 25 years, Joe gets to go free. Now, here's kind of a weird example, because what's the better payoff here? Well, a better payoff is going to be a lower value because this represents jail time. Okay. So the way that we'll solve these games is we're going to figure out what is Joe's best response to both possible strategy choices that Dan has, and then what is Dan's best response to both of the possible strategy choices Joe has. So let's start out assuming we're going to look at Dan's best responses. If Joe confesses, if Dan knew that, what should he do? Well, if he confesses, he gets 10 years. If he doesn't, he gets 25. 10 years in prison is better than 25. If Dan knew that Joe was not confessing, what should he do? Well, if he confesses, he gets 0 years. If he doesn't confess, he gets 5. No years in prison is better than 5. 0 years in prison is better than 5. So we've identified Dan's best responses to both of Joe's possible strategies. So here, notice Dan is always going to confess regardless of what Joe does. So Dan is going to have what we would call this dominant strategy. And to what? Confess. Okay. We're now going to figure out what are Joe's best responses. So if Joe knows that Dan is confessing, what should Joe do? Oh, sorry. I'm looking at the higher number. What's better, 25 years in prison or 10? 10? And then if Dan doesn't confess, what should Joe do? 0 years in prison is better than 5. So here, notice Joe always chooses to confess regardless of what Dan chooses to do. So here, Joe also has a dominant strategy to confess. So this is a not technical way of saying this, but when we're circling these decisions, these are the best responses. We said a Nash equilibrium is when we both are best responding to the other person's best response, or when we have two circles in the same box. A non-technical way of saying that, but that's what that would represent. So here we end up with this Nash equilibrium where both are going to confess. Okay. So we've got two dominant strategies that results in a dominant strategy Nash equilibrium. We also, this will be an example of a prisoner's dilemma, because a prisoner's dilemma is if we end up at a Nash equilibrium, where if we could change the strategy choices of the two individuals, we could make them both better off. So in this example, if we could somehow get them both to not rat on each other, to not implicate the other person, then we would be down here in this scenario where they're both not confessing. Both individuals would actually have better payoffs here or less time in jail. Okay. So because there's another combination of strategies where both people could be better off, but that's not our Nash equilibrium, that Nash equilibrium represents a prisoner's dilemma. Okay. All right. So that's kind of our setup example, right? So we identified, oops, kind of if Joe was confessing, what should Dan do? Right? 10 is better than 25 years in prison. If Joe's remaining silent, going free is better than 5 years. If Dan's confessing, what should Joe do? Confess, 10 years is better than 25. If Dan remains silent, what should Joe do? Whoops. He should confess, go free. So we had two circles in the same box up here where they're both confessing, right? And we said it's a prisoner's dilemma because if they could agree to remain silent, they could both have less jail time, right? Or both be better off. Okay. So sometimes we have these Nash equilibrium where they represent a prisoner's dilemma, and that's because there's always the incentive to be the one person that doesn't hold true to the agreement and doesn't, remain silent, or there's always an incentive to be the one that, implicates the other person in the crime so that they can go free. Excuse me. All right. So let's think about how this applies to duopoly models or oligopoly models and the market kind of structures we've been talking about. So remember from last class, I didn't have these two firm examples, but we had an example where I had like quantities and prices, and we were choosing the quantity that maximized profits for the monopolist versus perfectly competitive. So let's do that same example, but let's assume we have two firms and they're acting together as a duopolist. Okay. So if they acted together, the quantity that each firm should produce is 30. That would result in the quantity that the monopolist would choose. They would split monopoly profits. Okay. So the idea there being, if I'm looking for this Nash equilibrium, is this quantity decision actually the dominant strategy, or is that the best response of these firms when it comes to agreeing to work together as a cartel, right, or collude to get to the monopoly outcome? Okay. Well, let's instead assume they have this second choice. Now, obviously, in practice, we can go from 30 to 31 units. I'm only going to give you examples where we have two choices, right? So two different quantities. In theory, the same thing, the same results are going to apply. And I'll kind of give you a look into this in a second. If we had more than two quantity choices, but just for this, we got to walk before we can run. Let's just think about I can produce a low quantity of 30, or I can break the agreement and produce a slightly higher quantity of 40. Okay. So if I had that outcome, if I had those two choices, what are the potential outcomes going to be? Okay. So I've got here, if we both stick true to the agreement and act like a monopolist, we're going to split monopoly profits of 1,800, so both earn 900. If we both break the agreement and produce a little bit more, well, what's that going to do? Higher quantity in the market pushes down the price. Now profits aren't going to be as large, right? There's an output effect, but there's also a price effect, okay? And then if only one firm produces more, but the other keeps their quantity the same, what's the results of that going to be on profit? So where do these numbers come from? Well, first we'll kind of solve this game, and then I'll kind of make the connection to what we talked about last class, okay? So to first solve this game, and we're thinking about this as, actually, let me make sure I'm getting this in the right. Was it Verizon? Who is, okay. So we had T-Mobile, Verizon. They can produce a low quantity or a higher quantity. And then the resulting payoffs that we had were what? 900 and 900, 800, 800, 1,000. I think it was 750. Is that, I'm trying to make sure these match up with the slides here. Yeah. And then 750,000. Okay. So what is the optimal thing for do? Should both firms stick true to this collusion agreement and restrict quantity, push it back towards that monopoly kind of quantity in the market? Or will they break that agreement and produce more? So we'll go through this. What should Verizon do if T-Mobile sticks to that agreement and produces a low quantity? Well, if they produce a low quantity as well, they split monopoly profits. They get 900. If they produce a little bit more, well, the price in the market goes down a little bit, so that hurts my profits, but I'm selling way more units. So remember, profits are the quantity that I'm selling times the difference between price and average total cost. So even though by producing more, I'm going to lower the price in the market, if that's more than compensated for by the increase in quantity, my profits might be higher. So what should Verizon do? 1,000 is better than 900. What if T-Mobile breaks the agreement? Well, if I stick true to the agreement, when they produce more, the price would go down. I keep selling the same amount. What's going to happen to my profits? Well, they're definitely going to go down, right? From 900 to 750. So if they break the agreement, what should I do? Well, if I don't break the agreement, I get 750 as my profits. If I also break it, well, now, yeah, the price is lower, but at least I'm selling more units. I get 800. That's a little bit higher. Okay. And then, excuse me, what should T-Mobile do? If Verizon sticks true to this agreement and they do as well, they get 900. Sorry, 900. If they break the agreement, they get 1,000. 1,000 is better than 900. If Verizon breaks the agreement and I don't, I get 750. If I also break the agreement, I get 800. That's a little bit higher. So what do we end up with? This Nash equilibrium where we both produce a higher quantity. And is this a prisoner's dilemma? Yes, because if we did stick true to the agreement or we were able to get to some different combination of strategies, we could both be better off. Okay. So where is this really coming from? We can think about, oh, am I going to save myself enough room here? There we go. So quantity, price, here's kind of our demand curve, right? Here's our marginal cost, twice as steep marginal revenue. So if we acted like a monopolist, we were kind of thinking about, we were both setting the quantity to be equal to 30. So the monopolist quantity was 60 total quantity in the market. That would result in some corresponding price here, right? If we were producing 30 units, and then we could kind of compute those profits that ended up being 900 each. Okay. If one of these firms breaks the agreement, what's going to happen? Well, now the total quantity in the market is going to be what? 30 plus 40. So now that's kind of quantity. The second quantity is going to be 70. Right? We know that that's going to result in a lower price. Well, the lower price is going to hurt the profits of both firms. But remember, the quantity of one firm isn't changing at all. This was only if one of the firms broke the agreement. So what's definitely going to happen here, the profits of the firm that break the agreement goes up. They're selling more units. They've compensated for this reduction in price. But the firm that kept quantity the same, this lower price is going to result in their profits being lower. Well, the Nash equilibrium pushed us out here to an even higher quantity. Right? So we could even think that this is our Nash equilibrium, where we're both producing 40, so the total quantity in the market is 80. The price is even lower because we're both producing more, and we're getting pushed towards what point? What does this point represent? Well, if this marginal cost, right, if this was a monopolist, we said that was the supply curve, the point where supply is equal to demand, this was going to be the quantity of a perfectly competitive market. What are profits of a perfectly competitive market? 0. So there's always this incentive for both these firms to break that collusion agreement, which pushes us towards that long run perfectly competitive quantity, or pushes firms towards profits of 0. So I only did 2 production decisions here. Well, now notice I could say, okay, what if I produce 50? Well, now there's an incentive to be the one that breaks the agreement, produces a little bit more. We end up with a Nash equilibrium where we both produce 50 and then 60 until we get to that quantity where profits are equal to 0. Okay? Once we get to that point, why would it stop there? So to just kind of give a little bit of an insight as to why we would stop at the perfectly competitive point. So it doesn't matter if I have Verizon or T-Mobile. So think about this as like, I don't know what quantity this is going to be. Something like 190 and 190. Quantity of 200 and 200. Firm, this is what? Was Verizon on top? No, T-Mobile. Doesn't really matter, but Verizon and T-Mobile. So what's going to happen is, right, instead of going from 30 to 40, this kind of idea continues until we get to quantities where potentially maybe here we're both earning 100 or 100 million. If I'm the one that produces a little bit more here, maybe this is I don't know, 150. What do I want this to be? Negative 50, negative 50, 150, right? And then if we both produce 200, we're at that perfectly competitive outcome where profits are 0. Well, if we went through and solved this model, what ends up being true? When T-Mobile is setting the quantity of 190, what should Verizon do? Produce a little bit more than they are. What if T-Mobile is setting at 200? Well, 0 is better than negative 50. And then if Verizon's setting the quantity at 190, what should T-Mobile do? Produce a little bit more. If they're producing more, what should T-Mobile do? Choose 0. So we end up getting pushed to this point where perfectly competitive profits are equal to 0. And we know it won't go any further than that, because if we continue to go past 210, what's going to start to happen to quantity at quantities higher than this combination of 200, 200, so quantities greater than 400? Well, their profits would start to be negative. Well, now there doesn't exist an incentive, right? 0 is higher than a negative value. So this is kind of where that long run equilibrium will kind of end up at. Okay. So kind of good news is that as long as we have free firm enter and exit and firms can make this production decision, there's the incentive to always be the one that breaks the agreement. And that thought process would continue all the way down to always be the firm that's producing a little bit higher of a quantity until we get down to that point where profits are equal to 0, or we're at the perfectly competitive outcome. So the fact that this is kind of our long run, this is our Nash, or fact that we have a Nash equilibrium that is a prisoner's dilemma when we have these collusion agreements is good, because it pushes that long run outcome to be where profits are equal to 0 for both firms. Okay. So if I was looking at this in kind of table format, and I can kind of keep this as constant marginal cost, we can think about this in a slightly different, or visualize it in a slightly different way. So let's say I had the perfectly competitive market. What would the price and quantity be of the entire market? So even if I didn't have revenue or marginal revenue, remember, how did we find revenue? Total revenue, that's just price times quantity. And then what is marginal revenue? It's the change in total revenue divided by a change in quantity. Well, here I have changes in the quantity of 1,000. So, that's a little bit more difficult than the ones where we had like changes in quantity of 1, but I could still compute these columns. We did stuff like this last class. Okay? So what would the long run perfectly competitive outcome be? Well, if I've got a constant marginal cost, so I've got this quantity, price, so I've got my demand curve, I've got a constant marginal cost of 50, all right? I can think about I've got my marginal revenue, which should be twice as steep, right? That quantity the monopolist chooses should be where marginal cost is equal to marginal revenue. They go up to the demand curve to set the price. The quantity of a perfectly competitive market is, well, if we're in the long run, we have constant marginal costs, right? That really represents our supply curve. So supply would be equal to demand. The perfectly competitive quantity is out here. And with horizontal marginal cost or constant marginal cost, the price is set right at that point as well. So if we're looking at that table, how do we match this up to our visual? Well, a couple things to point out. I'm kind of rehashing things from module 11 here. But every time the quantity goes up by 1,000, how much is the price going down by? Or how much is the demand curve decreasing by? Looks like 10 every single time. So what should marginal revenue be falling by every time we go up by 1,000 units? Well, it should be twice as steep. So marginal revenue should be declining by 20. Sure enough, it is. Okay. So where does marginal cost hit our demand curve? Well, remember, price quantity, this is our demand curve. So it's going to hit the demand curve at that price of 50. So the total quantity in the market would be 1,100. Nope. Sorry. Was it 11,000 or 1,100? No, oh. It was 11,000. Sorry. 11,000, right? Which means how much is each firm producing? Well, it would be the total quantity in the market. We have these duopoly models, so just half that. Okay. So this would be my perfectly competitive outcome. If each firm is producing 5,500, the resulting price would be down here at 50. What are the profits of each firm going to be? Well, if profits are equal to the quantity I'm selling times the difference between price and average total cost, we said in these models where we have constant marginal cost, every unit has the same cost. So my per unit cost, it'll be the same thing as the price. I end up with 0 profits. Okay. Now, if they were acting like a monopolist, they should set the quantity where marginal revenue is equal to marginal cost based off of the entire demand curve, right? So we have the perfectly competitive market. What if we now look at this? If they're able to act together as a monopolist, where would marginal revenue be equal to marginal cost of 50? Looks like it would be here at 6,000 units. They would then go up to the demand curve and charge a price of 100. Okay. So the quantity that the monopolist would choose, or if their firms are acting together as a monopolist, they would want the total quantity in the market to be 6,000. They went up to the demand curve to set that price. Okay. And just to kind of, the perfectly competitive price here was 50. So notice, what's the quantity that each firm is going to produce if they act like a monopolist? Well, it's going to be the total quantity in the market. There's 2 firms, so they're splitting it evenly in these models, so 3,000. So each firm should be producing 3,000 if they're holding true to this collusion agreement. Now, as a result, what are profits? Well, we could calculate them, right? Difference between average total cost, which with constant marginal cost, that would just be our marginal cost. So 50 times what? 3,000. That should be our kind of monopoly profit. So 50, well, I'd have 4 zeros and a 15. So 15, 1, 2, 3, 4, 150,000 should be the profits of each firm. Where was I getting that? Price was 100. My constant marginal cost was 50 times I'm producing 3,000 units. That gave me that profit of 150,000. Okay. So each firm, so the total quantity in the market 6,000, but each firm, yes, they're still charging that same price of 100, but they would each be only producing half of the total quantity in the market, or 3,000. Okay. So I want to give a little bit of insight here. So why does breaking that agreement, why does it make sense, right? So there's a couple different ways of thinking about this. Let's say one firm produces a higher quantity, right? So instead of producing 3,000, they produce the higher quantity of 5,500. What that would do is push the market to what, 8,500 if I add those together? So potentially, if only one firm breaks the agreement, so I don't know, we'll kind of call this break, we'd be at 8,500 total in the market. That would result in a lower price. So I don't know, call this, I don't, we could actually figure out where it's at on the demand curve. Do I have the demand 8,500 is, no, not quite. So it's going to be somewhere between 80 and 70. So we'll say 75, right? So notice the price is lower. So the firm that kept selling 3,000 units, they now keep selling the same 3,000 units, but instead of 100, the price they're charging is only 75. So the profits of that firm that didn't break the agreement will go down. The firm that did break the agreement, yeah, they're losing money by selling this now at a lower price, but they've increased the number of units they're selling, right? So it would have to be that that output effect is larger than the price effect. That way, the firm that broke the agreement, their profits would be higher. The firm that didn't, their profits are lower. That's what gives us that normal form game matrix that we were looking at like the T-Mobile Verizon example, that makes it so there's always this incentive that pushes firms away from this monopoly point. There's always the incentive to be the firm that produces a slightly higher quantity. But if we both have that incentive, we end up with this prisoner's dilemma, Nash equilibrium, where it pushes us down to this equilibrium quantity. It's not equilibrium, sorry. Pushes us down to this perfectly competitive equilibrium quantity. Okay. There's another way of thinking about this as well that's a bit more extreme, but I think it helps solidify why we end up seeing these duopoly models end up at the perfectly competitive point as opposed to being able to agree to work like a monopolist. So let's instead say I've got firm one and firm two, and I don't know, just to kind of, we'll just choose two prices. One is higher than the other, one is lower, right? So I'll think about the most extreme scenario so that it really highlights this fact. And then if it wasn't as extreme, we get the same kind of results, but it would just be less pronounced. So one thing that I'll do here that I think I'm going to show you, I've got some quiz questions, is I don't always kind of draw these in as kind of the diagonals. Sometimes we're just going to represent firms' payoffs and separate them by a comma. I prefer this. But if you look out there, most game theory stuff, they kind of use that matrix, where we've got kind of the diagonals. So let's say we both set a high price, and I don't know, this is thousands, so like we get $100,000 each, right? If we both set a lower price, well, maybe this is like, well, what do I want here? Let's say we both set a lower price. Let's say we would earn nothing, okay? If firm one is setting a high price and firm two sets the lower price, right? Well, the reason why profits were zero for both firms here is because when we're both setting the same price, we're splitting demand evenly. If I'm the one that's charging half as much for that good, what's everyone going to do? As long as we're selling the same good, everybody's going to want to buy from me. So even though I'm selling at a lower price, everybody is now buying that good from me, right? And then the person setting the higher price, nobody's going to buy it from. Well, I'm earning zero revenues and I have some costs. My profits end up becoming negative, right? Same idea here. If firm one sets the lower price, everybody buys from them. Nobody buys from firm two. They still have their costs. So we'd have something like this. So if we solve this game, if instead of thinking about setting the quantity, we think about it as though they're setting the price, trying to like undercut each other's price, what should firm one do? Well, if firm two chooses the high price, firm one should choose to set a low price, right? If firm two is setting, because it's always better to be the firm that's selling it a little cheaper because everybody's going to want to buy it from me. If I'm setting a low price, firm two setting a low price, what should firm one do? Well, if I set a high price, I don't sell anything and I just have my fixed costs. If I lower the price as well, we're splitting demand and my profits are zero, but zero is better than a negative value. Okay. And then what if I'm thinking about firm two? Firm one sets a high price. What should firm two do? Well, 150 is greater than 100. If firm two sets a low price, zero is better than negative 50. So what do we end up with? This Nash equilibrium where we're both best responding to each other's best response, or a prisoner's dilemma, Nash equilibrium. It's a prisoner's dilemma because if we could somehow agree to keep the price higher, we could both be better off. Okay. All right. Any questions there? Oh, before we keep moving here. So why would this result where we like collude with each other and act like a monopolist not hold? And it's really because, like in this example I just showed you with prices, or we kind of built it out with quantities, there's always the incentive to be the one that breaks the collusion agreement, which pushes us, it's a dominant strategy, and it pushes us down to this dominant strategy where we both break the agreement. Not better for both firms. In fact, it's an example of a prisoner's dilemma. They're both worse off. However, there is that incentive that pulls them away from that combination of strategies where they could have earned higher profits. So we've got a prisoner's dilemma that pushes our firms towards the perfectly competitive quantity and price. So, it's not necessarily, the profits won't be lower than the competitive. They'll end up being exactly the same as perfectly competitive profits. It doesn't create any additional competition. It's just that each individual has an incentive to be the one that breaks that agreement. And then firms knowing all the offers are illegal, so they break the deal. That's not the reasoning behind why. It's because we have this dominant strategy in this game that these two firms are playing. Okay. All right. So we already kind of walked through. I showed you some of these duopoly cooperation examples with price as opposed to quantities. I also kind of took these and kind of mapped them out into a normal form game with quantities. So that's kind of why I had this slide left open. Okay. What do I want to do here? We will. So I know I want to go through that. I want to do that one. We'll talk through these and then we'll go to the quiz. So what are some other examples we see of the prisoner's dilemma, just to kind of give us an idea about how these principles, these things we're talking about, will be applied in real life? We could also have examples like with ad wars. So there's always the incentive to be the firm that spends a little bit more money on ads, because if I spend more money than the other company on my ad, more people are going to want to buy from me. So even though I'm increasing my costs, right, I'm keeping the amount I'm selling, I'm increasing my output. However, if every firm has that incentive, everybody spends money on ads, it kind of negates, right? Each one cancels each other out. We both still keep splitting demand evenly. We've just increased our costs. So we're getting the same amount of revenue as before, but higher costs. What have we done? We've decreased our profits. So essentially, there's always the incentive for a firm to be the one that's spending a little more on advertising. So we end up in this prisoner's dilemma, Nash equilibrium, where everyone's spending more money on advertising, eating into firms' profits. Well, once again, the prisoner's dilemma isn't always a bad thing. In this case, just like with our collusion agreements, it pushes us towards a perfectly competitive outcome. Here, you could argue, well, it pushes us towards more ads. That's a bad thing. It's just wasting resources for society, right? But it doesn't allow for there to be like one dominant firm. So, here we don't get quite as nice of an outcome, because the Nash equilibrium is that everyone spends money on ads. That's money being spent on ads. It's like, there's a big argument, like, is that beneficial? Well, maybe it allows consumers to know what products exist. That discussion gets a little bit more nuanced. But we're thinking about here, firms would just be spending money on things that don't actually improve, right, the quality of the products for society. OPEC is another example. that we see. You have all the member countries, and they try to act like a cartel. They try to come together, have this organized body so that they can boost profits for everybody. But quite often, you see kind of countries kind of breaking that agreement, producing a little bit higher of a quantity than what they agreed to, setting lower prices, and it's all because we have these prisoners' dilemmas in terms of the strategy choices of these companies, okay? Or countries, I should say, in this case. Military spending. It's always better to be the country that spends a little more on your military. So what happens? Everyone has this incentive, pushes us towards this point where countries spend a lot of money on their military. Once again, you could argue this is a bad thing, right? We're getting a bad outcome because all this money that could be spent on other things to improve people's lives is going towards these huge military budgets. So another example of prisoner's dilemma. One that we've already talked about are common resources. So this is the idea. Oh, I could probably even kind of give you a quick and dirty example here. So this is kind of a dumb one, but let's say we have person one and person two, and they're fishing a pond, and it's completely free, right? It's non-excludable, but it's rival that when I catch a fish, nobody else can, right? So if we both agree to catch one fish, right, every single year, we might be able to catch 10 fish apiece, right? Now, if we both catch 2 fish a day, or whatever this is, maybe this is if I catch 1 fish today, over the next week I can still catch 10 total. If we catch 2 a day, well, now the fish population, or maybe this is every year, it can't repopulate. So when people keep more fish every day, the ultimate, the benefit, the total benefit overall is, well, those fish go away, right? In fact, in the most extreme example, if we both catch 2 fish, there's no more fish left to repopulate. We could end up with kind of the future payoffs being 0, right? So if we then think about, all right, if I catch 1 fish a day and the other person catches 2, right? Well, if they catch 2, I'm like, they're going to be maybe better off, right? I'm still catching 1, but now I can't catch as many future fish because the fish can't repopulate as much. So it would have to be something that where the other person's overuse of the common resource, because it's rival, prevents me from potentially kind of being able to catch as many fish. So maybe this is like -5. I catch my 1 fish, but now there aren't as many fish left in the future. And then here, same kind of idea. The person that catches more currently, they're happy, but people in the future can't catch as many. We could kind of go through, solve this game. So we have what? Firm 1, 2, and then we have, if they choose to do this, what should firm 2 do? Or firm 2, person 2. We end up with this Nash equilibrium where we both overfish because we don't want to be the one person that doesn't. We end up with kind of this outcome where we're both worse off than if we could both hold true to the agreement and not overuse this common resource. Okay. Now, we could end up with a scenario, it doesn't have to necessarily be the case. A lot of common resources we see fall victim to the prisoner's dilemma. But just to kind of point this out, if we had kind of a similar setup, so we start out with 10 and 10 here, 0 and 0, but let's say this was 15 and 5. Well, now if we go through and solve this game, so what should player 2 do? 15 is greater than 10, but now 5 is greater than 0, right? And then what should firm 1 do, or person 1 do? When the other person is catching 1 fish, they can catch 2, catch 1. So it's possible that with these common resources, we actually end up with multiple Nash equilibrium, which is going to be that one person overfishes while everybody else kind of sticks true to that agreement. Okay, so it just depends on what the payoffs are to both of these individuals. But here's a situation where we haven't looked at one like this yet, where you can actually have multiple Nash equilibria. Okay, so this is an example where we have multiple equilibrium, just like some of the other stuff in economics we talked about. this would result in the answer being, well, what are we going to see play out? It's indeterminate. We don't know which of these scenarios we're going to end up in, but we know once we're in one of them, there's no incentive that kind of pulls us away from that, right? So if we were here, should player 2 change their decision? Nope, 0 is better than 5. Would player 1? Nope, 15 is greater than 10, so we'd stay here. If we're over here, should firm 1 change their decision? Nope, 0 is worse than 5. Would firm 2? 10 is worse than 15. So once we end up in one of these equilibrium, we're going to kind of get stuck there, right? But we don't know which one we're going to get stuck with. Okay. All right. So I kind of already discussed this, right? But like in these additional prisoner's dilemma examples, maybe there's things that are going to reduce social welfare. So like we overuse a common resource. You could think of like where was some of those that, well, it was like a negative externality we talked about with common resources, or these ads, spending wars, or the military arms race. That's probably wasting resources in society. It's probably a bad thing. But when it comes to our markets, and we're thinking about firm production and price, production decisions and pricing decisions, it pushes towards a perfectly competitive market, which should be doing what? Maximizing total surplus. So if we had a market that was a monopoly, another firm enters, even if they agree to act like a monopolist with the other firm, we know that there's the incentive to break that agreement, and it pulls us towards that perfectly competitive outcome where total surplus is maximized. Okay. So what else do we want to say here? So instead of doing an example with this, maybe we'll touch on this again next class. I want to do this one, but I think before we do, let's take a look, just working through more examples of these normal form games. And one of the ones that we're going to look at here in a second is a little bit more interesting. So let's take a look at these. And I'll just draw them out for us. So we're going to have them here on the quiz. I don't know. I think me being able to point to stuff is kind of helpful. So we've got United. They can either cut fares or not cut fares, right? And American kind of has the same idea. So this is kind of like a price setting example, right? Cutting fares means that, okay, I now have the cheaper flights. If I don't cut fares, right, mine remain kind of higher. So I'm going to write these down, and I'm going to ignore the millions. I'm just going to use the values. It won't change anything, right? It just changes how many trailing zeros we have. So if I looked at this game, what is the Nash equilibrium? Okay. So if United decides to cut fares, what should American do? Well, 400 is greater than 200, so they should also cut fares. If United doesn't cut fares, what should American do? Well, if they cut their fares, right, they can sell to way more consumers, even though they're selling at a lower price. In this example, they would have higher profits. Okay. What should United do in response to both of American's decisions? Well, if American cuts fares, so should United. If they don't, United should cut their fares. So what do we have? United always cuts their fares. American always cuts theirs. So we have basically this kind of dominant strategy equilibrium where both firms have a dominant strategy. And this is going to be an example of a prisoner's dilemma. Why? Because if we could agree both to not cut fares, we both could be better off. Okay? So this is another good example of kind of our prisoner's dilemma. Now, the next problem, so this is the one, looks like stuff we've already done. The next problem is a little bit more interesting. So instead of thinking about this in the terms of a firm level, let's think about this in terms of like workers and individual decision making. Okay. And this is really, if you kind of took it, there's just a class only on game theory, and you would start to dive into these issues, it becomes pretty interesting to kind of analyze individual decision making. So let's say you have a decision between working hard and what we call in labor economics, they kind of label this as shirking. All that means is like you're slacking off, you're not working hard. So if these are the two choices that each of these workers have, And I always like think about this example. I like to use it because I probably mentioned this before. I used to work at a grocery store, right? And stocking shelves. And there was definitely people I worked with that shirked a lot more than they worked hard, right? And so this example we can think about for person one, if the other person is working hard, well, if I slack off, I know that the job isn't going to get done. The job might require two people to be done like very well. If I'm someone who really cares about what my boss thinks or really wants this job to be done well, then even though the other person's working hard, if I slack off, although it's nice to not work, I am really dissatisfied that it's not done correctly. And so if I was also working hard, it would actually give me a higher level of total utility. So think of this as representing the total utility to both of these workers. Okay. Now, if person two is shirking or not working hard, well, once again, it's nice not to work hard, but I really value making sure my boss thinks that I'm getting this job done and that the job is being done right. Now I know I can't do it completely all on my own, but I know that at least something will get done. So in this scenario, worker one, regardless of what the coworker does, they're always choosing to work hard. They get some internal intrinsic utility from the fact that this job is done correctly, which pushes them to always work hard. Now, if we look at the slacker, right? Person two, okay, well, they like to keep their job, like they don't want to lose it. So there's some value they get in working hard because, the boss thinks they're doing well. But if the other person's already working hard, if I'm going to kind of get credit for what's being done, I really value kind of kicking my feet up and not having a hard day at work. I might find it in that scenario more, generating more utility for myself if I kind of slack off or shirk. And then what if the other person is shirking? Okay, well, I do like to, slack, I like get some value of kicking my feet up and not working. But if the other person's not working as well, I don't want to lose my job. So maybe in that scenario, I would choose to actually work hard because I want to make sure I don't lose my job, that something is getting done. Well, in this scenario, what do we end up with? So it looks a little bit different than the other games that we've looked at. We still have a Nash equilibrium, but it's not a dominant strategy equilibrium because what person two does depends on, right, what person one is doing, right? It does now, they're not kind of in the same column here. So what do we end up with? We end up with this Nash equilibrium where the person who valued working hard more ends up working hard, and the person who valued kind of slacking off a little more ends up slacking off. Okay? So we don't always have to have these equilibriums, Nash equilibriums, be where both people choose to do the same thing. It can be a different combination of strategy choices here. Okay? Now, would this be an example of a prisoner's dilemma? No, because there's no other outcome. So here they'd both be worse off. Here they're both worse off. Here, one of them is better off, but the other person isn't. So we actually need an outcome where both are better off. So this would not be an example of a prisoner's dilemma. Okay? So for that first one, we said we had that Nash equilibrium that was a prisoner's dilemma where they both cut fares. In this example, player one or person one worked hard, person two shirks. And then we have one more example where it's not as extreme as what I drew it earlier, but we have kind of firms setting prices. When you think about which of the following is true or not true. So if I've got this example, we have, oh, well, we'll make it colorful. Why not? So we got firm one. They can set a high price or low price, high price or low price. So I did one like this earlier, but this one won't be as extreme, kind of where profits were zero. So I've got firm two here, got 10 million, 10 million, 7 million, 7 million, 5 million, 15 million, 15, 5. Okay. So you'll notice in a lot of these games, we have symmetric payoffs, right? That doesn't always have to be the case. We just looked at one where they weren't, right? But if we did, we go back to this example. We can solve this once again. So if person 2 chooses a high price, what should person 2 do? Set a low price. If person 2 sets a low price, what should person 1 do? Will also set a low price. Right. If person 1 sets a high price, what should person 2 do? Set a low price. If person 1 sets a low price, what should person 2 do? Set a low price. Okay. So what are we ending up with? A Nash equilibrium where we both set a low price. It's an example of a prisoner's dilemma because we both could be better off. So if we're thinking about which of the following is not true in that participation quiz example, well, they both had a dominant strategy. So this was firm 2 was always choosing a low price. Firm 1 was always choosing a low price. So they both have a dominant strategy. It's going to be an example, so they won't cooperate and set a high price because the Nash equilibrium is for them both to set a low price. It's going to be an example of a prisoner's dilemma because if they would both set a high price, they'd both be better off. The Nash equilibrium results in total profits being maximized. Well, no, total profits for the firms are actually both lower, right? So that's going to be the one that's not true, right? So it's going to be sometimes our Nash equilibrium was actually end up in this prisoner's dilemma where both firms are worse off or their profits wouldn't be as high as if they could somehow both agree to keep setting that higher price. Okay. All right. So that should do it for a quiz here. So we had what? Equilibrium. That's not going to maximize our total profits. Did I forget to select one? We'll see. No. Yep. So we got all three of those. Okay. All right. So we'll do extensive form games next class. I want to run through this example and show you maybe how things could change here. So let's assume we have a research and development example. So if both firms, if one firm invests in R&D, everybody, if there's no patents, everyone can use that technology, and we would both end up with 10 million additional dollars, right? We're both selling more products because we're both using this new, whatever it is, the new product they came up with, cost-cutting technique, etc. So we would both earn 10 million. Now, research and development costs 9 million. And then if both firms invest in the R&D, we now, don't come up with the same thing. So we've got multiple new products that we can mimic and multiple everything. Now we could maybe both receive 15 million. Okay. So if we both put money into R&D, we both earned 15 million, but it cost us 9, so we both got 6 million additional dollars. If we both don't put any money into R&D, things stay the same. There's no change in profits. If Toyota doesn't put money into R&D, so they spent 0, but they get to mimic that new product or whatever it is that Ford came up with, they get 10 million. Ford gets 10 million as well, but they spent 9 million in R&D, they only get net $1 million. And then the flip, if Toyota invests, but Ford doesn't, Toyota only gets 1 million, Ford gets 10. Right? So if we had this game, oh, I'm bad at drawing those and signs. So let's think about invest. So we had what? Ford and was it Toyota? So we have, if they both invest into R&D, we had what? 6 million additional profits. If they both don't invest, 0. If I'm the one that invests, but the other person doesn't, I only get 1 million, they get 10. And then same kind of idea here. If I don't invest, but I steal the technology of the firm that did, I get 10, they only get 1. So if we go through and solve this R&D game, what is Ford's kind of optimal? Okay, if Toyota invests, Ford should not invest. If Toyota doesn't invest, then Ford should invest. What should Toyota do? If Ford invests, they should not invest. And if Ford doesn't invest, excuse me, they should invest. So here in this research and development example, we actually end up with multiple equilibrium, kind of similar to the game we looked at earlier. Now, we don't know which of these we're going to end up on, but we know we'll end up in one of them, right? Well, so we have one firm not investing here. For society overall, if both firms are investing, creating these new products, that could be, if we factor in what's best for society, not just these two firms, maybe we want to be in a scenario where everybody's putting money into research and development, coming up with new, life-saving products, etc. Right? So how could I ensure that I end up with a scenario where they're both investing? Okay. Well, let's think about this. So let's say I had the same sort of setup, and I've got they can invest or not, they can invest or not, and I've got what? Toyota and Ford here. Okay. So let's say I put patents on things. Okay. So if I put money into this, right, nobody else can use it. Right. So that would be the idea that Toyota invests right into this R&D, and they get before it was like creating 10 million for both companies. Maybe now they get all 20 million and they spent 9, so that would do what? That would give them 11 million, right? Now if Ford doesn't invest, they're going to get nothing. And then if Ford invests, right, they're now going to get 11 million, right? If they don't invest, Toyota gets nothing. Now, if they both don't invest, we're back at 0, right? So what would happen if I have these patents? Well, when I invest and the other person does, right, I would kind of have, and this is going to be a weird one, but we could kind of think about if I can't use the other person's technology, well, then I still only get, an additional 20 million, but I had to spend 9, so maybe I'm only getting 11. Okay. So what could happen if we have these patents that protect this, right? Well, if I'm thinking about, let's keep my colors the same here, Ford, and I usually won't give you an example like this. I'm just kind of trying to push us a little bit. We actually have that Ford would be, or sorry, I need to keep red as on the top. Here, will Toyota invest or not? They'll invest. What about down here? Will they invest or not? They'll invest. What about here? What would Ford do? If Toyota invests, they would also invest. What if Ford, sorry, Toyota doesn't invest, what should Ford do? By creating a patent, right, not allowing the other company to use the other person's research and development, whatever they come up with, what did we actually do? We switched the Nash equilibrium from a point where only one firm was investing to where both are investing. Okay. Now, this is an extreme example, probably what could happen. Maybe if we both invest, we aren't selling 20 million additional, maybe we're only selling, 15. But even if these were both 6, we would still end up, we could draw this matrix back out. So I kind of looked at an extreme case here. Let's assume that we make this a little more difficult, which is that if we're both kind of coming up with this new product, so let's assume, I'm just going to start shorthanding. So invest, not invest, not invest. So 0, 0, 0, 11, 11, 0. Let's say I had changed the assumption that, okay, yeah, when one firm was investing into research and development, they came up with this new product, they're going to get a huge increase in sales. So that was 20 million minus the 9 of research and development. So they got an additional 11 million. Well, if we both come up with new products, people only have so much money. We're not both going to make 20 million. Maybe we only both make, let's say, 14. Well, we both make an additional 14 million, but we had to spend 9. So what's the kind of net gain there? Well, in fact, we could kind of do an extreme. Let's assume if we both come up with a good, not only are we going to make, let's say we're only going to make 10 million additional, right? We both come up with a new product. We're splitting demand again. We spent 9 million. We're only getting an additional 10 million. So each of us is only going to have a $1 million benefit. So even under that extreme scenario where there's like we're evenly, splitting a pie evenly, and that if I, it's not going to be like we both make an additional 20 million. If we both put money in, we have to kind of split that 20. And so we're each only making 10 minus our cost of 9, we'd be at 1. Well, notice it doesn't matter. As long as we have that patent, what's going to happen? Okay. So if I think about Ford and Toyota, if Toyota invests, what should Ford do? Invest. If Toyota doesn't invest, what should Ford do? Invest. If Ford invests, what should Toyota do? Invest. If Ford doesn't invest, what should Toyota do? We end up with that same Nash equilibrium that even if there aren't these crazy high gains to research and development, as long as the benefits to research and development when we both put money into R&D, as long as it's greater than our costs, we'll always end up with these patents in this Nash equilibrium where we both invest, which is better than for society where only one of us invests. Okay. Excuse me. And you could, imagine a scenario where, first of all, any questions? I know I'm kind of throwing a lot at you. I start to get kind of excited about this stuff because, like, this is stuff plays out in the real world, right? So we kind of talked through there can be multiple Nash equilibrium. This is going to look similar to like a chicken game. So this is I introduced the idea of both running at each other at the beginning of class. We can either both, if we go left and right, good outcome. If we both go left, we crash. We both go right, it's we crash. There we would have kind of multiple equilibrium in a game like that as well. Okay, so I'll draw out two things for us here. Let me get my mouse out of the way. So the first is, because I did this for the other section, so we'll start with this and then we'll kind of come back to the more R&D side of things. So let's say we think about, so why are these called chicken games where we end up with multiple equilibrium? Well, because it kind of originates with that schoolyard, like, kind of childish game of chicken where we both run at each other. If we both go left, negative payoff to both of us, right? We crash into each other. If we both go right, negative payoff, we both crash into each other. If I go right and you go left, well, there's no real benefit, but at least, we didn't crash into each other. I could even put this here at 0. If we go through and solve this game, what should person 1 do if person 2 goes left? Well, intuitively we know, well, if I knew they were going left, I would definitely go right. And if I knew they were going right, I don't want to crash. I definitely would go left. I don't have a dominant strategy. Person 2 has the exact same kind of thought process, right? If I know person 1's going left, I definitely don't want to crash. I'm going to go right. If they go right, I don't want to crash. I'm going to go left. We end up with this kind of multiple equilibrium. This is why we call them like chicken games. Okay. All right. So something else that might mimic more what you see without patents, right? So I said in this example, without patents, it could be a chicken game, right? There's enough money to be made out there that in this scenario, one firm is going to invest, the other's not, right? It's not great. It's not both of them investing, but at least we have somebody putting money into R&D. We could end up in a scenario. So let's think about invest, don't invest, invest, don't invest. So let's say the payoffs, if we both don't invest, no additional costs, no additional revenues. Okay. So now I want an example where, let's say when I come up with this new product, let's say we could both make 10 million on it. Oops. Remember, that was what I said before. Sorry. But in my kind of previous example, we said, what did I want? I said in that case, so let's say if I'm investing and we both can use this, there's no patents, we both make 10 million. And let's say at R&D, the cost to R&D was, I don't know, let's do 12 million to make a point. Okay, well, if firm 1 invests and firm 2 doesn't, Firm 2 gets 10 million additional dollars, but notice firm 1 is only going to get negative 2 million. If firm 1 doesn't invest, they get $10 million when firm 2 invests, but firm 2 loses 2 million. Now, if they both invest, there's like an ample amount. They won't both earn 10 million. We said they would both earn 15. So when they both invested and each one had a cost of 12, how much were they both making? 3 million. So if the costs were in such a way that it only makes sense for us both to invest if we can get this higher amount. So this was like when we both invested, there was like a multiplying factor in terms of how much additional revenue we were earning. Well, now notice what's my Nash equilibrium if that was the case. So firm 2 invests, firm 1 should not invest. If firm 2 doesn't invest, what should firm 1 do? Not invest. If firm 1 chooses to invest, what should firm 2 do? 10 is greater than 3, so not invest. If firm 1 is not investing, what should firm 2 do? 0 is better than negative 2. Under this scenario, when costs to research and development are higher, we don't end up with multiple equilibrium. We actually end up with one equilibrium, and that equilibrium is an example of a prisoner's dilemma. So with R&D, we can see it be this like chicken game, but if the costs are high enough, and we don't have patents, we could also see that we end up with this Nash equilibrium that's a prisoner's dilemma where neither invest. And then we also had, if we have patents, we can kind of change that Nash equilibrium to be where they both invest. So just trying to kind of think about if we can understand these games, if I'm the government or I'm trying to regulate these markets, I can start to make decisions based off the costs and the benefits I see out there that would push these firms towards these equilibriums. And, if I'm the government, I don't care necessarily about the firms. I just care about which of these outcomes is going to benefit society overall. Okay? Any questions before we keep moving there? Okay. All right. So next class, we have time. I'll probably revisit this. It's another prisoner's dilemma example. It's not, I don't know. It's interesting, but to me, it's not, we've done so many of these games, they're probably getting a little bit redundant at this point, all these prisoner's dilemma examples. I'll show you what this would look like if you had more than 2 decisions, right? So it basically just becomes more complicated, but we'll work through one that has no equilibrium. So there are some games, we didn't have one today, but we'll start out with one next class where you can have no equilibrium. And I'll also show you how you would kind of work through one of these games if you had more than 2 strategy choices using a very simple basic rock, paper, scissors game. And then we'll talk about extensive form games, right? So this is where decisions are made sequentially. And then I'll come back. I skipped over something here, which is if we have games that are played over and over, so not a one-shot game, but games that are repeated over time. Okay. And how that could change, how it could or couldn't change what our Nash equilibrium is. Okay. So we will do all of that on Monday. We should then have plenty of time to work through some practice problems and also start, like I said, module 13. Now that module reading isn't due until Tuesday because that's when we'll really dive into module 13 for the first time. Module 11 and 10 quiz and all the participation quizzes from this week due by the end of the day Sunday. Other than that, that should kind of do it for us here today. Gonna end the recording there. If you have any questions, I'll be hanging around. Feel free to ask